Taking our first look at hyperbolas in Chapter 9, Section 5, Part 1, still pursuing State Standard number 16. And let's watch, after we get the geometric definition of a hyperbola, let's watch one being drawn. But here is the scenario of what we're looking for. Hyperbola is the set of all points P in a plane such that the absolute value of the difference of the distances from any point on that hyperbola P to two fixed points, f sub 1 and f sub 2, is constant. Those fixed points, f sub 1 and f sub 2, are called the foci of the hyperbola. The line segments r sub 1 from any point to the first focus, and r sub 2 from that same point to the other focus, again, is called the focal radii. So this differs. From ellipses, we're not keeping a constant sum, but what's staying constant is the absolute value of the difference. So let's take a quick look at part of one being drawn. In this scenario, we're not going to see the entire hyperbola, but what we're going to see are the red dots representing just a portion of the branch. And so the distances that we have here from the focal radius, the constant difference is the same, and this is going to give us a half of the branch of my hyperbola as we watch that in action. Of course, the other half of the branch would be down here, and in this particular example, the x-axis is the axis of symmetry. So our hyperbolic shape has two branches. Each one kind of looks like a parabola, but not exactly. Each one then has a vertex and a focus that's inside the bucket, and the center is somewhere halfway between the two vertices. And in this case, there are only two vertices. Okay, so as we take a look at our formulas, don't forget, as we're going through this, either go to this web page to look at the formulas, or take the packet out and have that in hand as we're going through this lecture together, because that tells you all the formulas for hyperbola. Hyperbola in standard form looks very much like an elliptic standard form, with one difference, and excuse the pun, because this is subtraction, not addition, and subtraction, of course, we call the difference sign. So that little minor thing, if this were an addition sign, we would have an ellipse. This is a subtraction sign, we have a hyperbola. Now don't be confused. Make sure you look at your formula sheets. We do not determine which way the hyperbola is open by looking at the denominator. If you look at the formula sheets, it tells you whichever fraction is not being subtracted. That's the way we're going. Y is being subtracted, x is not being subtracted. Since x is not being subtracted, the x-axis goes horizontally left and right. Then this is a horizontally oriented hyperbola with its two branches, one opening left, the other opening right. Center is still pretty much the same as we would look for an ellipse, opposite of what's with x and y, so that's 2 and 5. A is the square root, now be careful here, A is the square root of the positive term's denominator. The fraction that's not being subtracted, we're going to take its denominator and square root it, and the square root of 1 is 1. A is always going to go the same direction that the hyperbola goes. B is going to go in the opposite direction. The square root of 9 is 3. Now for an ellipse, we had 4 vertices. Hyperbola only has 2. How do we know which ones they are? Well, it's horizontal. So going left and right 1 from the center will give me those 2 vertices. Only 2 vertices. Left 1, we subtract 1. 2 minus 1 is the 0.15. Add 1 to 2 and we get the other vertex, 3, 5, and that's all there is, only 2 vertices for a hyperbola, ellipsis 4. Here's another difference. For an ellipse, we subtracted the denominators and square rooted. For a hyperbola, we add the denominators and square root. So 9 plus 1 is 10. Square root of 10 is approximately 3.2. That's the distance from the center to each focus. Now think of it this way. We've got to go further out. So we get inside the bucket to the left, inside the bucket to the right. To get further out, we're going to add them together. For an ellipse, we had to keep them inside the shape, so we subtracted them. All right, let's go left and right 2 from the center to find our 2 foci. So 2 minus 3.2 is negative 1.25. 2 plus 3.2 is 5.25. There are the two foci. Eccentricity is still c over a. C in this case is the square root of 10. A is 1, so that's just the square root of 10. If we take a look at graphing, there's one other thing we need to find, and that's something called asymptotes. Now here's the formula. Y is going to equal plus or minus 3 over 1 distributed to x minus 2 plus 5. So if you look at your formula sheets, you'll see where this is coming from. So in the positive case, we're going to take this as 3, distribute that out as 3x minus 6 plus 5. We get y equals 3x minus 1 is one of our asymptotes. Now I know we haven't said yet in this lesson what an asymptote is, but we will as we graph. To find the other one, let's make this a minus 3 over 1. So that's negative 3 distributed to x minus 2 plus 5. Negative 3 distributed out to negative 3x plus 6 plus 5. So that's negative 3x plus 11. Those are the equations for our two asymptotes. Most likely I will not ask you for those equations, although some of your other teachers may. But we are definitely going to use them to graph. So as we get our graph paper, let's remind ourselves what our center was, 2, 5. So from the origin, right 2 up 5. From there, we're going to only find 2 vertices, right 1, left 1. Still only have 2 foci. Now before we get the foci though, we're going to go up and down 3. But I'm putting them in a light green color. Very light green color because these are not part of my graph. These will help me find the asymptotes in another way. So I find my 2 vertices by going left and right 1 in this case. The other 2 points I found by going up and down 3. If I consider those 4 points midpoints of a rectangle, and by the way, there's my 2 foci, so I went left 3.2, right 3.2 from the center. If I consider those 2 vertices and those 2 auxiliary points as midpoints of sides of a rectangle, and then that rectangle, I draw the diagonals and extend them through the corners of the rectangle, those are my asymptotes. And let's check to see if that's 3x minus 1. Well, that crosses the y-axis at minus 1, has a slope of 3, so up 1, 2, 3, right 1. Other one would be way up here at 11. We'll go down 3, right 1. We get our other point as well. All right, remaining thing to do is we've got to sketch our branches of our hyperbola. The hyperbola goes through the vertex, gets closer and closer and closer to the asymptote, never crosses, never touches, never gets parallel to it. I know that's difficult to draw. And our other branch as well. And you can see that our foci are inside the little branches or buckets, so to speak, of my hyperbola. And this was a horizontally oriented hyperbola. Now be careful. The way the rectangle goes is not the way always that the hyperbola goes. All right, let's look at our second example in standard form. And it's not the denominators we're looking at. That's what we were looking at for an ellipse. We're looking for which fraction is not being subtracted. We usually write that first. Since this is y, this hyperbola is going to open vertically, branches up and down. My center, be careful, the x value is over here with x. Don't just grab them from left to right. It's going to be negative 1, negative 3. I'm going to go up and down the square root of 25, because that's under y. And I'm going to go left and right, the square root of 16. So that's under x, we go left and right. Only 2 of these points are going to give me the vertices here. And those are the 2 points that we find by going up and down, since my hyperbola is going to go up and down. So if we go up and down 5 from the center, add 5 to negative 3 is 2. Subtract 5 from negative 3 is negative 8. Those are the 2 vertices. For the foci, we add the denominators. That's 41. Square root them. That's approximately 6.4 that we're going to go up and down from the center to find the two foci. But let's do that in our head. Add 6.4 to negative 3 is positive 3.4. Subtract 6.4 from negative 3 is negative 9.4. Those are my two foci. Eccentricity is still C divided by A. C, we're going to go exact, so that's the square root of 41 over A, which is 5. Some of your teachers might have you go decimals. If you look at your packet, the formulas for asymptotes are y equals plus or minus 5 over 4, that's A over B, distributed to x minus negative 1 plus negative 3. Let's distribute those out. Remember, subtracting a negative is adding a positive. Let's take the positive case. That's 5/4 that we're going to distribute out to x plus 1. Doing so is going to give me 5/4 x plus 1 1/4 minus 3, which is negative 1 3/4. In the negative case, distribute out negative 5/4 to x plus 1 is negative 5/4 x minus 1 1/4 minus 3 more, which is negative 4 1/4. I probably will not have you calculate those asymptotes for me on the graph, but for homework, you're sure going to plot them because they're essential for the graph. Speaking of the graph, our center is negative 1, negative 3. So let's plot that point, negative 1, negative 3. We need to go up and down 5 for our two vertices. We need to go left and right 4 for some auxiliary points to help us with the rectangle so we can draw the asymptotes. For the foci, we're going to go up and down 6.4 from the center. Alright, let's think of the blue and the green points as midpoints of sides of a rectangle. Draw the diagonals through those rectangles and extend them past the corners or the vertices of the rectangle. Those are my asymptotes. Since this opens up or down, I need a curve that goes through the top vertex, getting closer and closer to the asymptote, never crossing, never touching, never getting parallel to. And I need a branch that opens down that goes through the vertex. Notice that the foci are still inside the buckets as we speak. And there's drawing the asymptotes, the center, the two vertices, the two foci. So getting back to eccentricity, for a hyperbola, it's always a number larger than 1. And as we look at the table for everything, eccentricity for a circle, remember, was 0. For an ellipse, we had a number between 0 and 1. Parabola was 1. Hyperbola is greater than 1. And we have a theorem for both hyperbolas and ellipses that essentially tell us that eccentricity is calculated as c over a. Well, that's our first look at hyperbolas for today.